In the previous video, we considered the scenario where we take a C-shaped piece of wire and we're going to first turn on a magnetic field. So the C-shaped piece of wire is in the plane of the board and the magnetic field is coming straight out perpendicular to the board. Next, what we did is we took a metal bar and we connected the bar to the top and the bottom of that C-shaped piece of wire, and we allow this bar to move to the left or to the right. The first question we asked is, what is the rate of change of magnetic flux? So the rate of change of magnetic flux, change in magnetic flux over change in time. We did some algebra. We found that is the strength of the magnetic field times the speed of the bar times y being the height of the C-shaped piece of wire. The next thing we said is we realized a metal bar actually has some charges inside the metal that are free to roam around. These are the C electrons that we talked about in a previous chapter. When you have a particle that is moving through a magnetic field, that particle will feel a magnetic force. So we reason that the C electrons that are free to roam about that bar will be feeling a magnetic force and they'll be pushed in a certain direction. Now, technically, in nature, what happens is the electrons are the particles that are free to move around, but for many cases of what we consider, we could just as well pretend it's positive charges that are moving around. So for simplicity in this example, we placed positive charges in the metal bar, and we found that these positive charges are going to feel a magnetic force downward. So here's the force on the positive charges being down. Now we said this is the magnetic force that the charges are feeling. So okay, I could say F is Q VB sine theta. Now, what are we going to do with this? For the majority of this video and probably the next video, let's not worry so much about why do we care. Let's just go with the algebra, go with the reasoning, and we'll see where this leads us. So, okay, I have the magnetic force equation here, QVB sine theta. Now the angle between the direction of the velocity V and the direction of magnetic field B, V is to the right, B is out of the board. So we have sine of 90 degrees. That's just going to be the number 1. So I find the force on these charges could be written as F is equal to QVB. And I'm going to put a negative sign on the force because the force is downward. So, okay, there we get F is negative QVB. Now I look over here, I realize that I have a V and a B, the speed of the bar and the strength of the magnetic field. I have a V and a B over here. So let's just do some algebra and combine these two equations. Again, don't worry why we're doing it. Let's just do it and we'll see where it leads us. So I could write V times B is equal to negative F over Q. I could look over here and say V times B is equal to, I'll bring the Y downstairs on the other side. So change in magnetic flux over change in time. And then I have a 1 over Y when I bring it over there. Now, if I set the V and B, if I set them equal to each other, what I would get is negative F over Q is equal to 1 over Y times change in magnetic flux over change in time. And I'm going to isolate this rate of change of the magnetic flux. So I could write that as rate of change of magnetic flux to be negative F over Q times Y. So let's think about what we found. Okay, we said that we have a bar that's moving The bar is moving through a magnetic field. There are free charges in the bar that are free to roam around. So these free charges are going to feel a magnetic force. Now, if these charges feel a magnetic force, they will accelerate in a certain direction. And so if we're considering positive charges, the charges in this bar are going to accelerate downward. Is this what is definitely going to be going on in this problem? Let's consider what a different observer might see. So we are standing here, we see the bar moving. What if there's a small insect on the bar? So if there's a small insect on the bar, this small insect on the bar is going to be moving with the bar. So this small insect will be moving with the exact same speed as the bar is moving. So I could say a small insect riding on the bar will have the same velocity as the bar itself. And importantly, from the insect's perspective, the insect will not see the charges moving to the left or to the right. There are charges in this bar that are free to move the C electrons, the positive charges we're considering here instead of C electrons. But from the insect's perspective, these C electrons are not moving. So I could say from the insect's perspective, the charges in the bar are not moving left or right. Okay, what is a consequence of this viewpoint? Well, the insect will say that there is no magnetic force on the charges because from the insect's perspective, F we said was QVB sine theta, but the insect on the bar sees a speed of the charges as being 0. So the insect sees the magnetic force of 0. We see a magnetic force that is something that is not 0, something greater than 0. So I could say we see the bar moving to the right. We say there is a magnetic force on these charges. That is pointing downward. The insect still must see a downward magnetic force, but that force is not going to be the magnetic force. If a charge initially is up here and then that charge moves to the bottom of the bar, both myself and the insect should agree that yes, this one particular charge did move downward. But there's no reason that we are required to agree on what force it was actually causing the charge to move downward. So we see a magnetic force on the charges. What force does the insect see? Because the insect sees the charges are not moving to the left or the right, the insect sees a magnetic force of 0. So what force pushes down on the charges? From the insect's point of view, perspective. So what is the nature of this force from the insect's perspective? We say it's the magnetic force. What will the insect say it is? So let's just look at this result we had a little bit ago. So we previously said that delta phi b delta t is equal to negative f over q times y. What do we have here? Well, if you think back to material from exam 1, F over Q looks a lot like the electric field, because we said before that F equals QE from chapter 16. So, well, from there I could write that F over Q is really equal to just electric field. So I rearranged some of these terms, and I have something that looks like an electric field in this problem. So what the insect is going to see is the insect is going to see a downward pointing electric field. I'm going to leave some space here. I'm going to write above it in a moment. So the insect will see a downward pointing electric field. Okay, right now the argument that the insect actually sees this might seem a bit tenuous. So let's explore this term we have up here a little bit more.